Is the video which will give us the introduction to the series that we are about to start, and that is current electricity. Now, while in electrostatics we dealt with the charges at rest, but in this case, in case of current electricity, we'll be dealing with charges in motion. Now, usually what happens is that when we have a field setting, suppose we have a positive charge distribution on one side and the negative charge distribution on the other side, and we consider a charge, suppose an electron, and we know this from electrostatics that this electron will be accelerated by the field. Now the electric field acts from the positive towards the negative. Now, in the process, as the electron being negatively charged, the electron is attracted by a force Fe, and that Fe is equal to the charge of the electron and the electric field that is applied, but is directed opposite, means it is attracted towards the positive plate. Now this constitutes this motion constitutes what we know as the electric current. Now, what is this electric current exactly? So the current, in any language or any other term that we can see, the current is just a flow. So the current deals with the flow of anything. Now here in electric current, or the current electricity part, we are associating the flow of charges. Now obviously the charges cannot flow on themselves, they flow under the influence of some field. Which is mainly the electrostatic field in this case. And this electrostatic field, as you know, is due to the charge distribution over here and over here, that is on the left hand side and right hand side, with the positive and the negative charge distribution. And however, one thing I can say, or we usually say, is the conventional flow of current. Now usually it's very necessary to understand this. The conventional flow, anything that flows must have a higher side and a lower side. So anything that flows, a fluid, we usually observe it to be flowing from the higher side to the lower side. And here we, in electrostatics, we denote the positive side as the higher potential, to be at the higher potential, while the negative side to be at the lower potential. So by convention, what we know is that anything that has to flow must flow from the higher potential to the lower potential, and that is what we say is the conventional flow of current. Now that is the case of with positive charge. So obviously a positive charge will flow from the positive side, from the higher potential to the lower potential. But that is not the case that we observe usually, because in reality the electrons, being in the free state, in the free or in the conducting state, are available for the flow of charges, for the conduction of current or the flow of charges, for the conduction of current or the flow of charges. Now this current that flows or the conduction that occurs due to the flow of electrons obviously happens that the electrons are flowing from the lower potential to the higher potential. So the electrons, they flow from the lower potential to the higher potential in this case. Okay, so although we have the conventional current, the conventional current is where the positive charge flows from the higher potential to the lower potential. The negative charge flows from the, this is the higher, this is the lower potential, suppose the negative charge will flow from the lower potential to the higher potential, and usually this is the case because the negative charge or the electron is available for conduction. It is in the free state, while the positive charge in the form of a proton lies inside the nucleus. The positive charge, that is the proton, that is available in case of an atom, is inside the nucleus, and for a solid packing, for a solid state, usually in the form of wires, the nucleus won't move because the atom on the whole does not move, and that is why this flow of positive charge is not usually the case. The usual case is the flow of electron from the negative to the positive terminal. So this, although this must occur, but this is the case where the negative charge flows in the opposite direction, right? Okay, so let's move over to the next page. Now obviously with the cases of the higher potential, the cases of the higher potential and the lower potential, in both these cases what we find is that there has to be a potential difference, usually denoted, the potential is denoted by V, V standing for voltage, the symbol. So as the potential is measured in voltage, so we use V as the symbol for potential. So there has to be a potential difference in order that this thing, this flow of charge is a so potential difference is a necessary condition actually for the flow of charge to take place. Now we we usually observe in a conductor. So let's take the case of a wire, cylindrical wire. This is a highly magnified view of it. So this is probably a conducting wire, and it has free electrons, and this is a segment of a wire and it has free electrons in it. Now, as we have these free electrons available for conduction, now with the positive and the negative terminal provided, the electrons tend to move along this direction. We'll be discussing detail for the drift speed that we will be obtaining uh, just a few minutes later. But as of now, what I can say is that the amount of charge, so the amount of charge takes a certain time, a certain amount of charge takes a certain amount of time to move from one point to the other point in a conductor. In this case, the electron moves from one end to the other end. Let the ends be, suppose, B and this be A. So in order to move from the point B to the point A, we have a certain amount of charge and they take a certain amount of time. Amount of charge divided by time taken for the charge to flow from one end to the other end is what gives the measure of current, usually denoted by I. So this is the formula for electric current, which is simply the ratio of the amount of charge that has flowed, from one end to the other end, from one end to the other end. Now, as we are considering this, what we have over here is that it may so happen, now this is the calculation for the average flow of current. Now the average flow of current is I equals del Q, that is the amount of charge that has flowed, divided by del T, that is the amount of time that has been taken. Usually what we have observed, as in case of the kinematics part as well, the average velocity and the average accelerations, just like that. So this is the formula for average current. But what about the it is obviously not possible for us to calculate the total amount of charge that has flowed from one end to the other, right? Because you cannot really calculate that the this many amount of charge was flowing from one end to the other, and now the ammeter does not do that. What does the ammeter do? Now the ammeter calculates the instantaneous current. For those who do not know, the ammeter is a device which is used to measure the current. So instantaneous current is something which is determined by the ammeter at any instant of time, a very particular instant of time, what is the amount of current that is flowing through the wire, because the charge is usually we cannot measure the amount of charge that is flowing. Although on the other hand, by knowing the instantaneous current, we can make an assumption of the amount of charge that has flowed within a given time interval. So usually this formula that we have over here, usually that is not the case. The case that we have with us is the instantaneous current. I write I in as the subscript or the um notation for the instantaneous current. So I instantaneous is given just in the same way as we did for kinematics. We have limit del t tends to 0 because this time becomes really infinitesimally small, so that we can squeeze it to a particular instant of time. So the average part that was there, that is del q by del t, for del t limited to almost 0, we have the value for the instantaneous current that is given by dq by dt, that is in the form of derivatives. So this is the expression for the average current that for the instantaneous current that flows through a wire subjected to obviously a certain potential difference, and we can obviously measure the amount of charge now that is flowing within a given interval of time. Now suppose the instantaneous current is varying with respect to time. I take an example for it. Suppose the instantaneous current is varying with respect to time, which is given by suppose let us say it is 2t square plus 4t plus 5 amperes. Now we want to determine how much amount of charge flows across the wire for this instantaneous current, which is varying with time as shown, and let the time interval be equal to the we want to determine the amount of charge. So the amount of charge that flows within the conducting medium conducting medium for a time interval, say from t is equal to 1 second to t is equal to 2 seconds. We keep it simple. So in that case, what we have is we can use this formula over there that we have obtained. Now usually we do not need that instantaneous subscript over there. We understand that this is varying with time, and we can obtain this value. So between t is equal to 1 second to t is equal to 2 seconds, we can obtain the value as I being equal to dq by dt. We have dq, that is the amount of charge, to be equal to I times of dt. Now we can write I explicitly, and from that we have, for value of I that is over there, we have 2t squared multiplied with dt. I write it uh, in the expanded form, that is 2t squared plus 4t plus 5 whole multiplied with dt. So that gives me the value of dq. We can obtain the entire q by integrating dq, and we integrate it from the given limits. So it is from 0 to q in this case, and the time is integrated from the given variation that has been that is there in the question, that is from 1 seconds to 2 seconds. So with that expression at the top, we can bring it over here. We have 2t squared dt, and this is integrated from 1 to 2 seconds, plus again 4t dt. The 4 can be taken outside, the 2 could have been taken outside as well in the previous term. So 1 to 2 over there, and then finally what we have is 5 dt integrated from again from 0 to from 1 to 2, and then we have q to be equal to the value that is 2 stays out, t square is t cube over 3, the integration part, and that is from 1 seconds to 2 seconds, plus this is 4 goes outside, we have t square by 2, and this is from t is equal to 1 seconds to 2 seconds as well, and finally the last term is 5, and that is t over there again from 1 to 2. And integrating this by putting the values, what we have is q equals, now this is obviously 2 by 3 can be taken out, and what we have is t cube, that is 2 cube minus 1 cube, plus this is 4 by 2 gives me 2, and t squared is in the form of 2 squared minus 1 squared, plus the last term 5, and instead of t we can substitute 2 and the lower limit -1. And if you calculate this entire thing, what you have is 2 cube is 8, 8 minus 1 is 7, so 14 by 3 in the first number, 14 by 3 plus the second term is 2 times of 4 minus 1 is 3, so 2 times of 3 is 6, and finally you have the value as the last term, that is only 5. 5 times of 1 is 5, and so the total comes out to be equal to approximately 11 for this, and 4 2 by 3 for that, so 4.67, and so we have 15.67 as the value, 15.67. Now this is in amperes, so we have 15.67 amperes. I'm cramped with space over there, so I can just write it over here, the space that is available. So this is simply 15.67 amperes. Okay, with ampere being the unit of current. This obviously the electric current is a fundamental quantity, as we know. So the dimension is A or I in that case, and the unit is just that ampere. Whereas for charge, as we know from electrostatics, it is a derived quantity and it depends on it has the unit of coulomb and it has the dimensions of A times of T. Right, so although in case of the solids we have the free electrons as the charge carriers, because they are responsible for carrying the charge from one place to another because they are free, and so they can move. But in case of liquids and gases, as well as gases, in both these cases you have charged ions, positive or negative. Obviously ions means they are charged, so you have the positive and negative ions which move about following the laws of electrostatic attraction and repulsion along a given electric field to which they are subjected. Like in case of liquids, you have the suppose let us assume a conducting liquid which is usually termed as an electrolyte. The electrolytic solution such as copper sulfate, it provides positive ions in Cu++ and negative ions for SO4 minus minus, and as a result of that they tend to flow under the influence of the field. They tend to flow in opposite directions. The positive ions, they move along the direction of the electric field, while the negative ions, they tend to move in a direction attracted by the positive plates opposite to the electric field. While the in case of gases as well, when they are subjected to a certain potential difference, the positive ions and negative ions are formed, and as a result of that the current is conducted by both of them. Now it is important to know that stream of electrons also move in empty space. They can be made to move in empty space, and the steam in the form of gas, stream of electrons also can move in empty space, and they follow a definite direction as per the applied field and hence are able to conduct current. Now the electric current usually is represented by an arrow, as we are taking it from the from one end to the other, usually the case with positive motion of positive charge, or the opposite, the motion of the negative charge. It is from the higher potential to the lower potential, and it is usually represented by arrows. Now in this case, although it is represented by arrows which tell us the direction of flow, it is a scalar quantity. Now scalar quantity, because they are not left to themselves, they are drawn as per the alignment or the orientation of the conductor in which they are flowing. They cannot independently move outside the conductor as per the applied force and move in any possible direction, as in case of vectors, which have an independent direction, which have a definite direction to themselves. Now take for example, if I have the wire that I have drawn, the segment of the wire, and I happen to twist it along a certain line, the electrons or the charges that are flowing inside it, they will move within that wire, restricted to be placed within that wire, and they move along the wire as the direction provided. So they are simply following the motion that they have been provided, uh, but not as in case of, suppose, let us say, an independent particle in space which is applied with a certain force, and it has the option of moving at any given direction, and it chooses a certain direction, and as a result of that it has a certain displacement, and the displacement, well, it depends how the force has been applied, that whether the displacement is along the direction of the force or somewhere making certain angle with respect to the force, but nevertheless it is independent to move in free space in any given direction. So that is not the case over here. So that is why electric current is a scalar quantity. Moreover, the current is obviously given by the formula, charge over amount of charge over the time taken. Now the amount of charge over the time taken, the charge being a scalar quantity as well as the time being a scalar quantity, together they constitute another scalar quantity, which is the electric current on the left hand side. So with this we can move over to the types of current. Now although we'll be dealing with a steady current in most of the cases uh, for this chapter, but we have the types of electric current which we will be discussing in the chapters ahead. So the types of electric current being in the form of steady current. This is the steady flow of current, where the amount of charge that is flowing is usually the same over a given interval of time. That means the amount of charge flowing over a given interval of time does not change, meaning the current does not vary with respect to time, it remains constant. So which is mostly what we'll be studying. But we can have varying current, we can have any form of varying current, but that won't be dealt with in this chapter almost. Okay, so this can be the graph for a varying current, the plot for a varying current, where the current varies as the time progresses. And finally, another chapter that is to be dealt later is the alternating current. Now the alternating current, obviously, as the name suggests, its value alternates periodically over time. So as the time progresses, the value of current, we can say, if it had a certain value, let's suppose say this is at 0 and the value changed. Now we have all the zeros at the origin, the value changed, it increased to a certain value, and then there again back to its value of 0. after a certain interval of time. This is termed as the half cycle of the current, alternating current, and the other half, in the other half cycle, it goes to the negative value, and then again it is back to the origin zero value. So, and in both the cases we have the amplitude or the maximum value of current to be almost the same. This, if that is I0, this is minus I0 on the negative scale, and that is how we obtain an alternating current. So these are the various types of electric current that we have with us, uh, but we'll be dealing with mostly with this steady form of current in this chapter, right? So I guess that will be all for this video, and in the next video of current electricity we'll be discussing about drift velocity, drift speed, drifting of electrons within a conductor, and the various aspects that are associated with it. Till then, thank you for watching.